Okay. The first day you eat half of the pizza. The second day you eat 1/4 of the pizza. The next day you eat 1/8 of the pizza. Okay. The day after that you eat half of 1/8. So you have 1/16, right? And then you keep on doing that. Every day you eat half of the remaining pizza. If you can live forever, after many days, the piece of pizza you are going to eat is very close to the whole pizza, but still always have a tiny piece left. Okay. What I'm trying to say, mathematically we are trying to define what we mean by the total, what we mean by the sum of many terms. Okay. How to define? So now let's say 1/2, and then plus 1/4, and then plus 1/8, and then plus 1/16 forever. What is the meaning of the sum of infinitely many terms? So anybody want to guess the answer from the pizza question? So later on we are going to give the definition of what we mean by the sum of many terms and how to get the answer. So the total is 1. The total is 1, of course, right? You add up many pieces, 1/2, 1/4, 1/8, and 1/16, right? Eventually, if you add up infinitely many pieces, you have the total of 1. Okay. Very shortly, we are going to see that. Okay. So by that we mean we are going to define what is the meaning of the sum of many terms. That's the concept of series. I said series. Actually, that is the question we are going to motivate first. I'm looking for the handout. Now let me copy part 2 question 1. In part 2 we talk about series. By that we mean how to define. The part 2 is designed to motivate two things. One thing is how to define the sum of many terms. In particular, what is the sum of infinitely many terms. Okay, so that's one thing. And the other intention is to show you a super important series, so geometric series. Okay, we'll go over this question in very details. In many cases, we use the summation notation. Okay, the summation notation. We have seen the notation when we talk about the Riemann sum when defining the definite integral, right? This is the summation notation. So, but here we have many terms. You just tell me you just remember one thing. Okay, the one thing you need to remember is each value of I, each value of the index determines a particular term in the series. Okay. I will tell you the meaning. Okay. Now let's say when I'm not doing the question yet, I'm trying to tell you the meaning of the series. When I value is 0, when the index value is 0, it gives you the term determined by I value of 0. So do you see the value as 1? 1 is the term determined by I value of 0. So by that we mean 1/2 to the power of 0, I value of 0 will give you the term 1. Right. And then I value of 1 will give you the term. So now let's say 1/2. Okay. 1/2 is determined by I value of 1. So the term is 1/2. I think you can see the pattern. The summation notation, it means the sum. Okay. So the series, if you do not use the summation notation, the series, it means initial term 1 and then plus the next term 1/2. I'll call 1/2 term 1. Okay. And then the term after that, term 2 is going to be 1/4, right? So can I write 1/4 as 1/2 squared? you cannot write forever as long as you can see the pattern, and then you can use the dot 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 notation. Okay, so this one is not stopping anywhere. N can go larger and larger forever. Okay, you just use a notation like that to represent the series. Now I'm trying to say, you look at the mouse cursor, the summation notation and the dot dot notation. So these two notations, they represent the same thing. We call the thing a series. It's kind of a symbolic notation. So because I haven't told you the meaning of infinity sum yet. Okay, I haven't told you the meaning of how to add infinitely many terms yet. Okay, so very shortly we're going to define that. But this one is a symbolic notation. You can kind of imagine it means the sum of many terms, but for which we are going to define very shortly. Okay. At this point, I just want to tell you these two notations are equivalent, are the same thing. Okay, I'm going to tell you right now what we mean by the sum of many terms. We do not know the sum of many terms, but what we know is how to define the sum of finitely many of terms, no matter how many. Okay, so that's why. Okay, so how about we just now we can start to do question A. So when we do the question, we are going to see the meaning of many terms. Well, I mean the meaning of the sum of many terms. Okay. To define the sum of a series, we need to introduce a concept. It means the partial sum sequence. Given a series, we can define a partial sum sequence. Okay. So how about I still represent the series using the dot 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 notation. Okay, so basically I from 0 to infinity, 1/2 to the power of I. Each I value so determines a term. Okay, you do not list all the terms, you add all the terms. So that's the difference between series and sequences. Initial term is determined by I value of 0. So you have 1, right? And then the next term is determined by I value of 1. You have 1/2. The term after that is determined by I value of 2, right? So which is 1/4. I still write the form 1/2 squared. Okay, and then it goes forever. That's two representations for the same series. Now we are ready to do question A. Using question A, I'm trying to tell you the meaning of partial sum sequence. Okay. Partial sum sequence as 0 is the same thing as term 0. I'm going to call 1 term 0. I'm going to call 1/2 term 1. Okay. So first term is term 0. So I hope it's not too confusing. The first term is determined by the first n value of 0. Okay. So as 0 is the same thing as the first term, so which is 1. You haven't seen the meaning of the partial sum sequence yet. Okay. And then S1 is defined as, now listen to me carefully, so this thing is important. S1 is defined as the sum of the first two terms. Or you can think S1 is defined as the sum of term 0 and term 1. So which is 1 plus 1/2. I know it's possible to compute the answer, but for some purpose, I'm not computing this answer. It's because I want you to see the pattern. Okay. And then the next question is to ask you to compute S2. Okay. S2 Likewise, we call it the partial sum sequence. S2 is determined by term 0, term 1, and term 2. You add up term 1, you add up term 0, term 1, and term 2. You have S2. Okay. So S2 is computed using 1 plus 1 half and then plus 1 over 2 squared. Okay. So do you see S0, S1, S2 actually defined? So they are defined, right? So because each of these guys, each term in the partial sum sequence is actually the total of finitely many of terms. You have learned since a long time ago, the elementary school probably. Okay, you have learned how to compute the sum of numbers, fractions. Okay, I'm trying to say S1 is defined using the total of finitely many of terms. So is S2 and so on. Okay. Again, it's possible to evaluate the numbers. S0 is 1, S1 is of course 3 over 2, and so on. But we do not care about the numbers. The most important thing is the pattern. So very shortly, I'm going to tell you the pattern. Okay. Now, I think you can imagine it's possible to define Sn for any whole number value of n, right? So Sn would be the sum of term 0, term 1, term 2 up to term n. Altogether, you have n plus 1 terms. Okay, so we're done question A. When we do question A, I told you the meaning of the partial sum sequence. Partial sum sequence is formed by S0, S1, S2, S3 up to Sn. N can go forever, right? Each Sn is well defined, so because it's the sum of finitely many of terms is defined. Okay. After introducing the partial sum sequence, you listen to me carefully. Okay. Now let's say Sn, it means the sum of the first n plus 1 terms from the sum of all the numbers from term 0 to term n. Okay, you remember that first. After that, how do we define the sum of many terms? I mean, how can we define the sum of all the terms starting from term 0 goes forever to term infinity? I know term infinity, the term is not accurate, but I'm trying to say how can we define the sum of infinitely many of terms when I starting from 0 and goes forever. I'm trying to say how can we define the sum of, so now let's say 1 over 2 to the power of I when I goes from 0 to infinity. How can we define this? I'm trying to say how can we connect the series to the partial sum sequence. We mentioned before, so what is the tool to handle infinity? Here you also have an infinity, the sum of many terms, infinitely many of terms, right? How do we connect the two things? Anybody want to tell me how can we connect the two things? How can we connect the two things, please? The sum of many terms. So they on the left hand side you have the sum of infinitely many of terms. On the right hand side you have the sum of the first n term. I mean the first n plus 1 terms. How can we make the connection? So just tell me a term or tell me a notation. I'm missing something here. I'm missing something here. So what's the question mark? So please, you know that. Can you tell me the question mark? Can you tell me something to connect the partial sum and the series? The series itself, you interpret the series as the sum of many terms. What is the tool to
n?
So did you tell me n? What is n? An important concept we learned before to handle to deal with the infinity. How do you deal with what is the tool to deal with the infinity? I think I told you many slogans last time in Math 101, right? Sn is the sum of finitely many of terms. So this is the sum of infinitely many terms. Okay.
Limit?
Limit is right. So that's something I'm looking for, right? So does it make sense as long as you can get the partial sum sequence and then you take the limit as n approaches infinity, you have the sum of infinitely many of terms. The limit is the tool we use to deal with infinity. Okay. In this particular case, limit is the tool we define the sum of infinitely many of terms. So does that make sense? I hope. Okay. We just did question A. Sorry, I was trying to tell you what's going on. The idea. I think the idea is more important than doing questions. Okay. We just did question A. So very shortly, you're going to see what's going on with B, C, and D. Okay. Now let's work on question. Now let's work on question B. Okay. In question B, the partial. In question B, we are trying to compute the partial sum Sn. Okay. So how about we still use the dot 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 notation. Okay. Sn is the sum of the first n plus 1 terms, starting from term 0. Again, the convention in my course is the initial term is term 0. We always start from 0. Okay, it's easier for many things. Okay, you're going to see why. Okay. Now you see the pattern from question A. Sn is the sum of the first n plus 1 terms. Okay. So do you see S1 has 2 terms and S2 has 3 terms, and then Sn has n plus 1 terms. Okay. Using the definition, it's the sum of 1 and then plus 1 1/2. The term of that is 1 over 2 squared. I still cannot write forever. So because I don't know how large the value of n is. N could be 100, n could be 10,000. I don't have time to write 10,000 terms, right? I just use dot dot dot. Okay. Anybody want to tell me the last term? The last term, please. The last term would be 2 to the power of n. Okay. You see, for S2, the first term is 1, the second term is 1/2, the last term is 1 over 2 squared. The same is true for Sn. You just see the pattern from the particular cases. Okay. You know, in next step, we are going to take the limit of Sn, but it's hard to take the limit in this form. So before we take the limit, I'm going to tell you a super important formula. Okay, I will show you that on the next slide. You learn the following in junior high school, probably in junior high school. So, but it doesn't matter. You forget. I'm going to tell you why from scratch. Okay. So basically, so do you want to recall the formula? So now let's say 1 minus r and then times 1 plus r. If you look at textbook, so people have too many different ways to deal with this, but you just follow me. Okay, you just follow me. So what is formula for computing 1 minus r times 1 plus r? I think you have 1 squared, so which is 1. So do you just have 1 minus r squared? I was trying to use the formula like a minus b times a plus b equals a squared minus b squared. Okay. Your a squared is 1 squared, your b squared is r squared. I'm trying to use that to motivate a formula. Okay, very shortly you're going to see the formula, but still I'm trying to tell you why. Okay, so you have from here you have the formula. I'm trying to say 1 plus r is equal to on numerator you have 1 minus r squared, on denominator you have 1 minus r. So that's the formula for 1 plus r. By that we mean you divide two sides of the equation by 1 minus r, you have that formula, right? How about so did you learn a formula in junior high school or high school for computing this? At least you can multiply them out. At least you can multiply them out. Sorry, I did not see your question, Chad. I don't know your context. Your context, I mean. Okay. Now. Okay. At least you can try to multiply them out. Okay. Multiply them out. Or did you learn a formula for computing that? Probably you have. You learn a formula for computing a minus b. It doesn't matter. You multiply them out. Okay, you multiply them out, and then the thing you are going to get is 1 minus r cubed. 1 minus r cubed. Okay. And then the formula you are going to, and then I'm trying to motivate the thing I'm going to motivate is 1 plus r and then plus r squared is equal to, on numerator you have 1 minus r cubed, on denominator you have 1 minus r. I hope you can see the pattern. Okay, so this time if you want to add, now let's say 1 plus r and then plus r squared and all the way up to r to the power of n, what would be the formula to compute that? If you have two terms, 1 plus r, on the numerator you have 1 minus r squared, on the denominator you have 1 minus r. On this line, if you have 1 plus r and then plus r squared, the formula is 1 minus r cubed on numerator, and then you have 1 minus r on denominator. How about we add 1 and then plus r and then plus r squared all the way up to r to the power of n? The formula is going to be 1 minus r to the power of n plus 1, right? And then on denominator you have 1 minus r. That's a formula I want you to memorize. The formula is essentially coming from what you learned in junior high school. So what you learned, geometric sequences, geometric series. Geometric series. Can you remember the term? If you have a series, there's a common ratio. We call R the common ratio. You see the quotient between term 2 and term 1 is equal to R, right? I'm trying to say R divided by 1 is equal to R, and then R squared divided by R is equal to R. So basically the quotient between every consecutive two terms is equal to R. In this case we have a common ratio of R. R is the common ratio. And for geometric sequence with a, geometric series with the common ratio of R, the sum of the first n plus 1 terms is equal to that formula. Okay. You learn that in junior high school or high school. Chad, so do you remember that? I taught my math for teacher. Yeah, probably you covered that in math for teacher course. It's kind of the junior high school method, I'm pretty sure. In any case, try to remember the formula. Okay, we are going to use the formula to deal with many things. Okay, actually, the most thing we are going to cover today is to use that formula. Okay? After we know that formula, and then we can finish question one. Now look at question one. In question one, we are trying to compute the sum of this. Okay, the sum of this. So do you see that's actually a particular case when r value is equal to 1/2? If you add 1 and then the next term is r, again r value is 1/2, and then you multiply every term by r, you'll have the next term, right? Okay. In this case, we use the formula I just told you. You learned that in high school or junior high school. Okay. Again, r value is 1/2. So on denominator you have 1 minus r, so which is 1 minus 1/2, right? On the numerator you have 1 minus r to the power of n plus 1. So in this particular case you have 1/2 to the power of n plus 1. So that makes sense? No? R value is 1/2. We have a formula for computing the sum of the first n plus 1 terms in that series. So this one is a geometric series. Whenever in a series you have a common ratio, you have a geometric series. So we're done question B. So you have Sn in a closed form. You will have a formula for computing Sn, right? Okay, now we move on to C. In C, we are going to compute the limit of the partial sum sequence. In question C, we are trying to compute that the limit as n goes to infinity, as n gets larger and larger. We are trying to compute the limit of the partial sum sequence. So which means we are trying to compute the limit as n approaches infinity. Okay. On denominator you have 1 minus 1/2. I know it's possible to simplify, but I still want to keep this form. So later on I'm going to motivate something in general. Okay. On the numerator you have 1 minus 1/2 n to the power of n plus 1, right? Anybody want to tell me this limit? The final answer to the limit? You look at the mouse cursor, okay? So maybe it's yeah, the sum is 2. The sum is 2. Now I know what you mean, cat. The final answer is 2. Okay. Okay. Now you look at the mouse cursor, okay? The only term that is dependent on n is that term. All other terms are constant. I'm trying to say, you look at the cursor. That's a constant. That's a constant. That's a constant. Okay. The only term that is dependent on n is this term, is that term, right? So what is the limit as n approaches infinity of that term only? As n gets larger and larger, 1/2 to the power of n plus 1. I think we have seen the limit as n approaches 1/2 to the power of n. So that makes sense. This term gets smaller and smaller and tinier, closer and closer to 0. I'm trying to say as n approaches infinity, the limit of that term, you look at the mouse cursor, of that term only is equal to 0. So the final answer is 1/2. Okay. So the final answer is given by after this term, after that term, the limit of that term is equal to 0. Then the numerator it becomes 1, right? The denominator becomes 1 minus 1/2. Of course, the final answer is 2. It's 1 over 1/2. The final answer is 2. Okay. That's how we define the series. Okay. That's how we define the sum of many terms. Question A is nothing too important. I'm removing the answer to A. Okay. But I want to include the answer to D in here. Okay. Whenever the limit is a finite number, then we say the series is convergent. Whenever the limit is a finite number, so like this case, the limit is 2, okay? And then we say the series is convergent. Or we just say the series converges, okay? The series converges to 2. It's comparable to the term we used for improper integrals. Okay. Now we're trying to answer question D, okay? So maybe therefore, the series try to get used to the summation notation, okay? We're going to use the summation notation over and over again. The series converges to 2, okay? Or you can say the sum of the series is equal to 2. Okay? Yeah, probably you have seen that a long time ago. You have seen the answer a long time ago, okay? So basically, in addition to 1, in addition to this 1, you have the whole piece of pizza, right? I want to summarize the most important thing is how we define the sum of many terms, infinitely many terms. So by that we mean how we define the sum of the series. It's defined using the limit of the partial sum sequence. You imagine x is a constant. After we get the answer, we are going to treat x as a variable. Okay. I think we have seen the idea before when we talk about limit, the derivatives, right? Anyhow, we'll work on the question first. Okay. To determine if a series converges or not, the only tool we have now. Later on, you're going to have many other tools. Okay. The only tool we have now is the definition. We have to form the partial sum, right? We have to form the partial sum. We have to take the limit of the partial sum sequence, and then if the limit is a finite number, then we say it converges. When the limit is infinity or dne, then we say it diverges, and so on, right? In any case, we form a partial sum sequence first. Now the solution. We form the partial sum sequence first. Okay. We compute Sn. Sn is the standard notation. You do not have to tell me the meaning. By that I mean you do not have to say let Sn be the partial sum sequence, and so on. Okay. So because Sn is dependent on x, so can I use Sn of x to mean Sn is dependent on x? By that we mean for different values of x, you have different values of Sn. In any case, we just treat Sn to be the partial sum sequence, the sum of the first n plus 1 terms. Okay. When you see a notation like that, the term 0, you have x to the power of 0. We treat the initial term as 1. Okay. Initial term is 1. I'm going to use two notations to give you the representation of the partial sum sequence. One notation is the dot 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 notation. Okay, the dot 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 notation is you write the first few terms and then you try to identify the pattern. Okay, term 0 is 1. I'm trying to say the first term is 1. Initial term is 1. The same thing. I will call 1 term 0. Okay. The next term is term 1, it's x, right? X to the power of 1. You do not have to write to the power of 1, of course. The term after that is x squared, and all the way up to term n. Term n, I believe you have x to the power of n, right? Although we use the dot 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 notation, it's still finitely many of terms. I'm trying to say the sum is still the sum of n plus 1 terms, finitely many of terms. So it's possible to define that. It's well defined. Again, you do not have to. You just use one of the two notations. But in the future, I prefer to use the summation notation. I will give you the meaning using the summation notation. Okay, so basically, the line I'm going to write is the same thing as the line I just wrote in here. I'm just trying to use the summation notation to represent that. Okay, so this time you have try to identify the pattern. Actually, the summation notation can be identified from here. Okay, right. The summation notation. This time you want I, the index, to be changing from 0 to n. By that we mean the index value of 0 will give you 1. The index value of 1 will give you x term 1. Okay, I will write it down so you will see the meaning. Okay. The sum of the first n plus 1 terms can also be represented using a notation like this. I starting from 0, but here at this location you write n. The meaning of the notation, you let the index value of I run from 0 to n. Each value of the index will determine a particular term in the partial sum sequence. Okay. So you have x to the power of I, right? X to the power of I. I forgot to mention earlier. This formula I told you to memorize can also be represented using the summation notation. Common ratio is r to the power of I, and then if you let I run from 0 to n, again each value of I will determine a particular term. It's equal to 1 minus r on denominator. On numerator you have 1 minus r to the power of n plus 1. Okay. Again, in the future, I really want you to get used to the summation notation. Use summation notation whenever possible. Okay. Okay, so that's the partial sum sequence, and it's possible to compute that. So do you see, if you know this formula, if you replace r with x, you can compute the partial sum, right? So for this thing, on denominator you have 1 minus x, right? 1 minus r, and on the numerator you have 1 minus x, the whole thing to the power of n plus 1, right? Of course, anything on denominator cannot be 0. By that we mean the restriction should be x value is not equal to 1. Whenever x is not 1, then the formula is valid. In this case, I should have written r is not equal to 1. Okay, it's kind of by default. If you have 1 minus r on denominator, the denominator cannot be 0. So we have the partial sum sequence. Okay. When you are trying to determine a series is convergent or divergent, the first thing you do is to compute the partial sum sequence. So can I write step 1 to mean the first thing you do is to do that? Okay. And then the given series, I'm going to copy it down. Okay. I from 0 to infinity, x to the power of I. So again, we call this one a geometric series. The given series is equal to is defined as the limit of the partial sum sequence, the limit of the partial sum sequence as n approaches infinity. Okay, you have Sn of x is equal to, now we can plug the thing in, right? The limit as n goes to infinity, you just compute the limit of the following: 1 minus x on denominator, on numerator you have 1 minus x to the power of n plus 1. Okay. Do not tell me the limit right away. So because x can take any value at this point, x can take any value, so not equal to 1, of course. X cannot take 1. Now to get the limit, we have some cases. Okay. Again, the limit is taken when n approaches infinity. When taking the limit, you treat x as a constant. Okay. Still, we have some cases. The case is relevant to the limit of the sequence we mentioned earlier. Okay. So do you remember this case? Okay, we'll move on to this question, and then I'm going to review the cases. Again, the limit is only dependent. The only term that is dependent on n is that term. All other terms are constant if we treat x as a constant. Okay, x is not equal to 1. I said that many times already. Okay, and then the only term we have to take the limit is that term. Okay, I'm going to write the answer. You'll try to understand the answer. Okay, so there are some cases. So basically, when x is in between -1 and 1, when x is in between -1 and 1, like when x is 1/2, when x is -1/2, 0.3, 0.5, 5/3. So basically, when x value is a number in between -1 and 1, the limit of this term is going to be 0. You look at the mouse cursor, okay? When x is a value in between -1 and 1, the limit of this term as n approaches infinity is equal to 0. So the whole limit is going to be 1 over 1 minus x. So that's one case. You have comma here, you have semicolon here. That's one case. Okay. Actually, when x is any other value, the limit does not exist. You remember x cannot take the value of 1. X cannot take the value of 1. When x value is 1, the series is going to be the series like all the terms are 1, so the series is going to be like 1 plus 1 and then plus 1 and then plus 1, and all the terms are 1s, right? In that case, you can say the series is divergent. But when using this formula, x cannot be 1. Okay. There's only one case when x value is -1. But when x value is -1, so do you see the sequence is divergent? I want you to. The sequence is divergent. So like we mentioned here, okay. Or I can show you the case when x value is -1. Okay. You just remember the conclusion right now. Okay. When x is -1, the given series is divergent, or you can say the series diverges. You can say something like otherwise. Okay. To convince you further, so probably I can tell you some particular, I can show you some particular cases. A little moment. I'm going to copy this into here. To convince you more, okay. To convince you more, I will show you some particular cases. When x equals 1, and then all the terms in the series are 1, so the series becomes, it's not part of the solution, okay? The series from 0 to infinity, the series, it becomes 1 plus 1, and then plus 1. All the terms are 1s. If you imagine the partial sum sequence, and then the Sn is going to be n plus 1. So basically, you add up infinitely many of 1s. So this one diverges, of course, diverges to infinity. Okay, it's obvious. Okay. So that's the case when x is equal to 1. So now let's say when x equals -1, when x is -1, the series from 0 to infinity, it becomes, initial term I believe is 1, right? And then the next term is -1. The term after that is +1. The term after that is -1. And you keep on going. Okay. You see it's divergent. So the partial sum is going to be, the partial sum sequence Sn is going to be, so now let's say S0 is equal to 1, S1 is equal to 0, right? And then S2 is equal to 1, and then S3 is equal to 0. So basically it's divergent. So do you see it's divergent? Partial sum sequence is going to be alternating between 1 0 1 0 1 0 1 0. Right? It's divergent. Now let me show you one other case. One other case is when, so now let's say x value is 2. When x value is outside -1 and 1. Now let's say when x value is 2. So do you see the sequence now becomes from 0 to infinity, 2 to the power of I, right? Initial term is 1, the next term is 2, and then the term after that is 4, 2 squared, and then 2 to the power of 3. So do you see the series diverges to infinity? Right. If you add all the terms from 1 to 2, 1 plus 2 plus 4, and so on, it diverges to infinity. Or you can see it from the partial sum sequence, of course. I'm trying to convince you, okay, the series is convergent. It's convergent to 1 over 1 minus x only when x is in between -1 and 1. Okay. Diverges otherwise.